Hi, I am Rashani DeBell, and you are learning algebra. Hi everyone. In today's lesson, we are taking a look at scientific notation. Scientific notation is a method of writing really large or really small numbers in a way that we can understand it. So let's take a look at some of the rules of writing in scientific notation. Scientific notation. Our objective is to use scientific notation to represent numbers. What is scientific notation? Scientific notation is a way of writing numbers that are too big or too small to be conveniently written in decimal form. Scientific notation has a number of useful properties and is commonly used by scientists, mathematicians, and engineers. Writing numbers in scientific notation. Before we can write numbers in scientific notation, we need to know what a significant figure or significant digit is. Significant digits include 1, 2, 3, 4, 5, 6, 7, 8, or 9. Leading zeros are not significant. What I mean by leading zeros is something like 0, 0, 0, 1, 2, 3, 4. The first three zeros were not significant digits because they are leading zeros. A number written in scientific notation is written in the form of a point BCD times 10 to the power of n, where a represents our first significant digit. We have our decimal point. BCD are the numbers after the decimal, and they are the significant digits after the decimal. N is our exponent. Now let's look at some examples. To begin our examples, we start by rewriting in scientific notation. In our first example, we are asked to write 618 in scientific notation. To write this in scientific notation, we need to put our decimal point right after our first significant digit. Our first significant digit in this example is 6. We have an invisible decimal point right after 8, which we're going to make bounce and move it to the left twice in order for it to be between our first significant digit of 6 and our second significant digit of 1. So we're going to begin by moving our decimal point here twice to the left, which gives us 6.18 times 10 to the power of 2, since we moved this 2 spaces to the left. In our next example, we have 2.5. Notice that our decimal is right after 2, which is our first significant digit. So in this example over here, I really don't need to do anything to this number. Therefore, we are not going to be moving our decimal point any spaces to the left or the right. Our final answer is going to be 2.5 times 10 to the power of 0, since we're not moving the decimals either to the left or to the right. Here we have 0.00007245. In this case, our decimal has to go right past our first significant digit, which is 7. So it's got to go between 7 and 2. So I'm going to be moving this decimal, or making it bounce, 1, 2, 3, 4, 5, so that it can be between 7 and 2. Moving it 5 spaces. 1, 2, 3, 4, 5. When I do that, I get 7.245 times 10. And since I moved it to the right, it's going to be a negative exponent of 5. The way I can differentiate between a negative exponent or a positive exponent is by looking at the number. Usually when I have something like 0.00 or 0 point some number after the 0, in my head I look at it as a very small number compared to such a number as 618. So 0.5, 0.25, 0.75, 0.6. Those are really small numbers, and when I write those in scientific notation, my exponent is going to be negative because it is a small number, and that's the way I can remember when my exponent's negative or when my exponent's positive. Positive exponents are when your numbers are large, like 618, 2.5. Negative exponents are when your numbers are really small, like 0.000725. Here we have 310 million to write in scientific notation. I'm going to take my invisible decimal point that's all the way at the end of the zero and move it right over here between 3 and 1. So essentially, I'm moving the decimal 8 places to the left. Make it bounce. 1, 2, 3, 4, 5, 6, 7, 8 to get 3.1 times 10. This is a huge number, so my exponent is going to be a positive 8. Rewriting in decimal form. We have to write 7.29 times 10 to the power of 6 as a decimal number, or sometimes we call this standard form. One way of looking at this 10 to the 6th power is to think about it as 1 million, because this is basically saying you're taking 10 and multiplying by itself 6 times, and when you do that you get 1 million. So you're going to be taking 7.29 and multiplying by 1 million. Another way of looking at it is that you can take that 7.29, and since this is a positive exponent, positive numbers move through the right on the number line. So I'm going to take that decimal and move it 6 places to the right. So I'm going to make it bounce 6 times to the right. 1, 2, 3, 4, 5, 6, and every little bowl I have here, I'm going to fill it with a 0 to end up with 7,290,000. In our next example, we have 4.5 times 10 to the negative 7. This is a negative exponent, and since it's a negative exponent, I know that I'm going to be moving left on the number line, because all of the negatives, when the numbers are getting smaller, move to the left. So I'm going to take my 4.5 and move it to the left, and the decimal, so it's going to bounce 7 times to the left. 1, 2, 3, 4, 5, 6, 7. Every bowl gets a little cherry in there, and my decimal point is going to go between those two zeros so that I get 0.1, 2, 3, 4, 5, 6, 4, 5. So I have 6 zeros after the decimal point. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Just as a side note, this 10 to the negative 7 can be written as 4.5 times 1 over 10 to the positive 7, which is basically stating it's 4.5 times 0.0000 1, 2, 3, 4, 5, 6, 1. And when you multiply 4.5 times 0.000001, you end up with 0.00000045. And there's our answer. Computing with scientific notation. We are asked to evaluate the expressions and write the results in scientific notation. In these examples, we are going to utilize our knowledge of the multiplication, division, negative, and zero properties of exponents. In this example, we have 6.0 times 10 cubed times 2.4 times 10 to the power of 5. What I can do is use the associative property to group my constants and then group my base of 10s together and then multiply. So I would write this as 6.0 times 2.4 times 10 cubed and 10 to the power of 5. And the associative property of multiplication allows me to be able to do this. So I can multiply these together and I got 14.4 times, my bases are the same, so that just means that I'm going to add these exponents to get 10 to the power of 8. Notice that this 14.4 is not written in scientific notation. This means I need to move this decimal point over 1 to the left so that I have it in between my first significant digit and my second. And when I do that, I'm going to add a 1 to my exponent so that my final answer is written in scientific notation. So it's 1.44 times 10 to the power of 9. Here I have 3.0 times 10 to the power of negative 4 raised to the power of 3. I have parentheses in here, which means I need to distribute this 3 to every term inside the parentheses. And when I mean every term, I'm talking about every exponent. So there's an invisible 1 exponent right there that I'm going to multiply by 3. So this becomes 3.0 to the power of 3 times 10. Negative 4 times 3 is negative 12. I can evaluate this 3.0 to the power of 3. That is going to be 27 times 10 to the power of negative 12. Notice that 27 is not written in scientific notation, so I need to take my invisible decimal that's after the 7 and move it between the 2, which is my first significant digit, and the 7. And when I do that, I'm going to add a 1 because I'm moving it to the left to my negative 12 to get my final answer of 2.7 times 10 to the negative 11. In this example, we have 5.4 times 10 to the power of negative 2 divided by 7.2 times 10 to the power of negative 8. I'm going to write it this way. 5.4 times 10 to the power of negative 2 divided by 7.2 times 10 to the power of negative 8, which I can divide 5.4 divided by 7.2. And I know that since my bases are the same and they're being divided, that I'm going to subtract these exponents. So it's 10 to the power of negative 2 minus a negative 8. 5.4 divided by 7.2 gives me 0.75. And negative 2 minus a negative 8, remember, keep chop chop. This becomes negative 2 plus 8, which they're different signs, so I'm going to write this here, negative 2 plus 8, which simplifies down to 10 to the power of 6. Now 0.75 is not written in scientific notation, so I need to change that by moving this decimal over to the right by 1. And when I move it to the right, I'm actually going to subtract 1 from my original exponent value. My final answer would be 7.5 times 10 to the power of 6 minus 1, which is 5. And that concludes our lesson on writing in scientific notation. Thanks for watching.